Hello everyone, welcome to my channel Essentials of Electronics. In today's video, we are going to discuss about an application of op-amp. It is going to be a non-linear application. One of the best example of non-linear application of op-amp is rectifier. Yes, particularly precision rectifiers. A rectifier is an electronic circuit which converts AC into DC, that is AC sinusoidal wave is converted into DC pulsating wave. So we can achieve a DC pulsating wave by employing an op amp with a diode in the output. Yes, the resistor RL, an input voltage connected to the non-inverting terminal of the op amp, the diode D and RL is the load resistor V naught. Yes, what is the operation of this rectifier? This is the input voltage, output voltage taken with respect to time t. When the input supply voltage is fed, what is the input supply voltage? It is a AC sinusoidal wave. When the AC sinusoidal wave is fed in, what happens to the op amp with the diode? The positive signal during the first half cycle, the positive voltage is given to the non-inverting terminal. Thereby, the output voltage is positive here. This output voltage, positive voltage, forward biases the diode D. This forward biases the diode D and hence the output voltage will be same as that of the input voltage. So the output voltage is same as that of the input voltage during the positive half cycle. I repeat again, during the positive half cycle, which is fed to the non-inverting terminal of the op amp, the output voltage is positive. The positive voltage in turn forward biases the diode by giving a positive voltage to the anode of the diode, and hence the diode will be acting as a closed switch. Now the voltage V0 will be same as that of the input voltage, and hence we get an output in this manner as seen in the V0 graph. During negative half cycle of the input voltage, what happens? The negative voltage is given to the positive terminal of the op amp, and now the output voltage that is obtained here is minus V. This negative voltage, when fed to the anode of the diode, will reverse bias the diode. Negative voltage, when fed to the diode's anode, reverse biases and makes the diode act as an open switch. Now V0 is not connected to the op amp at all. So no output is generated during negative half cycle of the input. Yes, during positive half cycle, diode on. During negative half cycle, diode off. Again, during another positive cycle, we will be getting an output which is equal to the input. So by this way, the precision rectifier is capable of converting AC into DC. Yes, this is the output obtained using one diode. Next, we'll go to another circuit called ideal rectifier, which produces the same kind of waveform in the previous one. The previous one was a complete input sinusoidal was given, and we got only outputs during the positive half cycle, which means that positive output we get negative is 0. Again positive, negative 0, which means that the input sinusoidal wave has been controlled only for half of the cycles. Yes, the other half cycle is not obtained, which means that's the output of a half wave rectifier. Now, this is an ideal half wave rectifier. Yes, the previous circuit we had only one op amp and a precision diode. Here we have an op amp with two precision diodes. Let us check what would be the output. An input voltage is fed to the inverting terminal of the op amp through R1 resistor, compensating resistor for biasing purpose, load resistor, diode D1 and D2 with a feedback resistor RF. Yes, this is an ideal half-wave rectifier. We'll check on how to get the output waveform for this with respect to time, Vin. Vin is the sinusoidal wave which is fed into the negative terminal of the op amp. This is V0. What happens during positive cycle of the input? What happens during negative cycle of the input? When Vin is positive, when Vn is positive, the output voltage obtained at V0A is negative because the input is fed to the non-inverting terminal and D1 is forward biased. But still D2 is reverse biased and the output is 0. The output is 0. Yes. So when positive voltage is given to the op amp, positive voltage turns on the diode D1, but the voltage at this point is negative. A negative voltage makes a diode D2 to act as an open switch and hence no output is obtained during negative half cycle. Yes, during positive cycle, the diode D1 conducts and V0A is positive. When V0A is positive, a positive voltage is applied to the anode terminal of the diode D2 and hence D2 is forward biased. D2 is now acting as a closed switch when the input is negative and hence we get an output equal to the input but in a reverse manner. Again the cycle continues as long as we keep feeding an input signal, the output is 0 positive 0 positive. Yes, this is the output voltage obtained at the V0 terminal of the half wave rectifier. Even here we are getting only output for half cycles of the input. Hence, it is called half wave rectifier. So, I would like to state this portion as D1 on, D2 off. This portion is when we get negative cycle. So, it will turn off D1 and D2 on. This is an ideal of a rectifier. The op amp should be a high speed version as it alternates between open loop and closed loop operations. When Vi is negative, Rf is equal to R1 and the output voltage is positive, which in turn makes the output voltage even when the input is lesser than 0.7 volts. High slew rate is required as the input passes through 0 and V0A must change from 0.6 to -6 volts. If the diodes are reversed, negative output occurs. An inverting amplifier can be converted into an ideal half-wave rectifier by adding two diodes. The op amp in the circuit must be a high-speed op amp since it alternates between open loop and closed loop. For a negative input, that is Vi is less than 0, D1 is off, and D2 is on. The equivalent circuit for this circuit can be shown is the conduction states can be shown with the help of a circuit diagram. In this circuit diagram, we have two operational amplifiers. Where the input voltage is fed to the inverting terminal of operational amplifier A1, and the output of the operational amplifier A1 is fed to the non-inverting terminal of A2. They are fed at two different voltages, V and V. Output voltage 2 times of R. So the current through this I is equal to V by 2R. Vi by R current flows through the resistor. Yes, Vi by R plus V by 2R plus V by R is equal to 0, which will give us V is equal to minus 2 by 3 times of Vi. Then by applying in the equivalent circuit, we will be having D naught is equal to 1 plus R divided by 2R into minus 2 by 3 Vi. Yes. Now, when the operational amplifier 1 gives the output, the input signal is fed to the operational amplifier A2, and hence this is the input signal. During the positive cycle, the output voltage is negative. The negative voltage in turn is given to the positive terminal. Now the voltage at V0 is positive. During negative voltage, the output voltage at V0A is positive, and hence V0A gives a positive input voltage to the amplifier A2, and hence the output during the negative cycle is also positive, and hence we get a full wave rectified output. So this is the output of a full wave rectifier with two operational amplifiers. In the absence of precision diodes, we can connect two operational amplifiers and make it to operate in nonlinear application form. Thank you.